That's correct, yeah. Hi, everyone. I'm from Quantum Dice, quantum based on quantum physics, obviously. Dice, we produce random numbers, so that's the short explanation to what we do. Now, I'm going to talk about the two title slides that we have. I'm not quite sure why there is two, but let me just jump to the second one. So my talk is about self-certification for entropy generation. That maybe sounds quite complicated, but actually what it means is we want to answer the question whether it's possible to actually tell you if a random number is actually random. Sounds quite trivial, turns out it's not. I'm going to talk today about what entropy actually is. So some of you may have heard about this in the thermodynamics courses. I've seen Telefonica, they had a slide where they showed all of the different aspects of physics, so it's pretty much already answered. But yeah, I'm just going to talk about this in a, I guess, quantum random number generator perspective. How are random numbers used? Why is it important? Well, because in the end, we think that there's a great misunderstanding about what random numbers are, where they're used, and how they're used, and I think it's quite important to address that. How are they assessed to be of high quality? That's kind of what this talk is about. And obviously, I would be remiss to not talk about how our own quantum random number generator works, because it's a quite interesting technology, and it has very fundamental physics aspects, and it's trying to combine that with the real world. I think similar to what quantum computers do, and we face similar challenges. What is self-certification in a quantum context? And then I'm going to talk about use case and call to action. So let's start with entropy. So in our case, it is in principle a state of order or measurement of that, but for us it's just a measure of information. So we've heard before, bit 0, 1. That means two possibilities. If you have a fair coin toss, right, you'd get almost equally zeros and ones. If you take the logarithm of the maximum guessing probability of that, you'd get 1, right? So in this case, the maximum guessing probability is 50%. If you don't have a fair coin toss, and for example, all of the results are 1, your entropy is going to be 0, or very close to 0. Now, why is it important to have good entropy? And what are use cases for that? So let's start with, let's call it a dummy example. So let's take Portugal. By the way, happy 50th anniversary of the Freedom Day. If any Portuguese people are here, I don't know. Nice. So in Portugal, there's people, and if you want to, for example, have an understanding of how people are going to be voting for the next presidency, you're going to do a poll, right? So in the end, you'll have some sort of register where you have people, and if you have a bias in that, you're only going to be selecting people that are of a specific age that you meet at a market in Porto. Now, if you have a good randomness, then you have good selection, and therefore you have a good representation of the electoral outcome. Now, this is, as I said, a dummy example. Let's move on to the stuff that we're actually involved in. Let's start with encryption. So we've heard a couple of talks today talking about encryption, and I think the message that I want to get across here is that if you do not have a random key, and by that I mean unpredictable key, all encryption is kind of pointless. You can have the best algorithm if it's based on a key that's not random, then there's no way for you to actually succeed with that. Another very interesting use case is stochastic simulation. So we've already heard about that in the quantum computer context, but even in classical computing, right? There's a lot of use cases that require a good sampling of distributions using random numbers, using high quality random numbers. And for example, you can look at pricing financial derivatives. If you want to look at the stock, you price an option in the future, this is going to be worth X, right? How much, where are you going to put that price, if you try to create that option? And that is done using specific stochastic simulations. Most of them are Monte Carlo based, but there's also others. If you want to estimate whether you're an insurance provider, if you want to think about, okay, is this house going to be flooded next year? Is this forest going to burn or not? Right? You have to run some sort of models, and they're all based on a good selection of random numbers. We've heard about I guess drug discovery, molecules, weather forecasting, and even training AI models, especially like neural networks. They're all based on a good source of random numbers. Now, a question for the audience. Is this a random sequence?
Yes. Why not?
Okay. good. Is this a random sequence? Yeah, could be. Equal likelihood of that being random. However, this is actually pi. There's no pattern in this, but it's very well known, right? So I could tell you for this one and for this one, I could probably tell you the next one with specific likelihood, but depending on what that is, it could be, 1 over 9 or 1 over 10. Now, the interesting bit here is that typically randomness assessments are just based on detecting patterns. So for example, here I've highlighted 5 zeros or 5 1 and zeros. So, and the better we get at seeing what failures are caused by normal random number generators, the better our understanding is of detecting these within statistical assessments. However, they are not good enough to predict anything in the future. You could have a new way of failing, and they will. And over the last couple of years, we've always seen specific random number generators failing, and they just keep adding stuff to the tests. And even if you have a perfect random sample, there's still a specific probability with which you will fail, right? Because the test is designed such that a 0, 0, 0, 0, 0 would be flagged as a failure to some extent. However, there's a probability that this is actually the real outcome of a random process. Now, the main question for us is it possible to know something is really random? And we've also seen Schrödinger's cat here before. So the way a quantum random number generator works in principle is you have an inherently unpredictable process. And that could be based on anything, radioactive decay, for example. And then all a random number generator does in principle is it opens the box, it takes a measurement, and in this case, yay, our cat is alive, that's good, we send a 1. However, looking at the fact that we are all using realistic components, right? We're not using idealized components. We live in a real world, so there could be a communication issue. The camera could just say 1 because there's a bit flip. There could just be an image of a living cat in there, and the camera is just looking at the image. So there's many, many ways to fool a system and to, get rid of that assurance of randomness. So the question that we have asked ourselves is, how can a user actually know that a random number originates from this inherently random quantum process rather than from any electronic noise? And the way we do that is as follows. So in a typical quantum random number generator at the top, you have a source. You know what that source is. It creates a quantum process, or it enables a quantum process. That could be photons, it could be anything else, right? You take a measurement and you draw entropy from that. Entropy, again, is a distribution from which you can draw random numbers after some post-processing. But I put entropy plus because there's much more than just the quantum aspect in that, right? Because you have real measurements. Now what we do is let's jump the source for now. We also have some sort of source that enables the process. But we have quantum process A. We're going to take a measurement. That measurement is a certification measurement, and it looks at a very specific aspect of this quantum process. Now, in the meantime, there's a quantum process B, which is dependent on the previous process, from which then another measurement draws entropy. So the measurement of quantum process A infers a specific value to the measurement of the entropy generation. That means you then get both essentially a distribution of entropy, but you also get a value, a very specific value that you cannot change, that informs you how much quantum entropy there actually is. Questions now or later?
Just a quick question. The arrow between quantum A and quantum B, is this a quantum error or a classical arrow? Is this a measurement and classical information, or is this a quantum link?
This is a quantum link.
Okay,
yeah. And then what you get in the end is a certified min entropy. That means you actually know how much quantum entropy is within your system at any given point in time. And now the bonus thing is, I put a question mark here, is you don't even need to have control over the source. I could give everyone in this room access to the source. You can just put whichever state you want in there. But by having this cascade, you're actually allowing me to always know how much entropy is in my system, which avoids like silent failure and these kind of things. Now currently, the hardware is used, for example, in hardware security modules or as a hardware root of trust, where we manage security functions with telecommunications providers or banks, or we also have a entropy as a service instance, where this follows a NIST standard, where we have different hardware units as their own instance, which send both certified random numbers, the live verification signal, and test results, whichever the user requires, directly to the local user, who can access this very easily using like /dev/random, for example, and then use this in their crypto protocols, or also for their simulations. And the interesting thing is that, you know, within the crypto protocols, it's kind of a question of trust. How much trust do you put into specific statistical assessments? How much trust do you put into this system? And that's, you know, that's a very debated question. That's why standards are quite important as well. But for simulations, we're going to publish a paper next week, which shows that you get a very good advantage by just using quantum random numbers versus any other random number generators. You can speed up simulations 30%, 50%, and that's, you know, across very different types of Monte Carlo simulations. So call to action, on the one hand, there's one that's hardware dependent. We want to create a specification for a stronger entropy assessment, because we think that FIPS 143 is not enough. So, you know, bringing that quantum aspect into the measurement. And then beyond this, we want to also build an open source entropy evaluation tool based on a suite of stochastic simulations to putting a number to the quality of random numbers. And we want to invite anyone that is a specialist in Monte Carlo simulations to actually, you know, work with us on developing this platform. So yeah, thank you very much.
Thank you.